Hello, everybody. I thought I should put this video together just in case you missed class or you needed a little bit more, maybe hear some of these things again that we talked about in class about intermolecular forces. They tend to be something that students struggle with at first, all right? So I wouldn't blame you if maybe you're swimming in some uncertainty, and if you need a little extra help, please always look for extra help. But maybe this video will help you. All right, now let's just say this quickly. We started off really this unit by looking at this simulation, PhET simulation, in which we saw neon and argon and oxygen and water. And we found that, I'm just going to say these things out loud, I'm not going to write this out right now. We saw that neon had very low melting points and boiling points, where water had an incredibly high melting point and boiling point. You know, compared to these substances, okay? And you can look back in your notes to see, you know, where those melting points and boiling points were, or if you want to look it up on the internet, sure, go ahead. But these guys versus water, they had very low boiling points and melting points. Okay, now let's be clear. When it comes to boiling points and melting points, we're really just looking at separation of particles. Okay, either particles separate easily, where, like we saw with neon, the particles separate easily, or it takes a lot of energy to separate those particles. That's all we're talking about. Okay. If you go from a solid to a gas, you're literally splitting up particles. So I wrote this out here. So neon was easy to separate, and I'm drawing like a little dashed line there showing the forces between those particles. Okay, very weak attraction there. Where here I've got these big dashed lines, and I'm showing a strong attraction here between these water molecules. So takes very little energy to separate neon, takes a lot of energy to separate water molecules. And to tell you the truth, this is why water is such a remarkable molecule. For being such a little molecule, it has incredibly strong attraction for its own molecules, okay? And in fact, when you look at the molar mass of neon, it's got a molar mass of 10 grams. No, it's got a molar mass of 20 grams per mole. And water has a molar mass of 18 grams per mole. Okay, so they're practically the same molar mass, they're practically the same size, but water has a huge attraction for itself. All right, why is that? So let's talk about the nature of intermolecular forces now. We're going to start our discussion of intermolecular forces with polar molecules, because these are the most easy, I think, to understand. Polarity. Now, I'm drawing an oval here. This is just a cartoon of a molecule. And in this molecule, we have a positive side and a negative side. This molecule is known as a dipole. It's a dipole because it has two poles. It has a positive side and a negative side. And that funny looking D, that's a delta symbol. That means partial positive charge and partial negative charge. It's not like a full-blown positive charge or a full-blown negative charge. It's a partial charge. And if I brought two molecules like this together, the positive side and the negative side would be attracted to each other, because positives and negatives attract each other. And that is the underlying principle in all of chemistry. Opposite charges attract and like charges repel. So much of chemistry is just about that. Okay? All right, so since we're talking about two dipole molecules, we would call this intermolecular force a dipole attraction. Okay? Dipole attraction. All right. So polar molecules are going to have stronger attractions for each other than nonpolar molecules. Okay, let's talk about nonpolar molecules now. All right, so I'm going back to the simulation that we saw in class, and we compared neon to argon. We found that neon has lower melting points and lower boiling points than argon. Okay, they're both nonpolar. Now, these are not molecules, they're just atoms, but I'm going to generalize this by saying molecules. Okay, if neon has a very low melting point and a very low boiling point, then we're going to see a weak attraction between those two atoms and a stronger attraction between the argon. Argon had a higher boiling point, higher melting point. So the first thing to understand, or to realize and to think about, is that neon has low boiling point, low melting point, lower than argon. Okay? Why is that? Because it all has to do with attraction between particles. Neon has a very weak attraction between other neon atoms. Argon has a somewhat stronger attraction between argon atoms. All right, it's easy to understand why that would be with polar molecules, because they have a permanent, they're permanent dipoles. Okay? If there's an attraction between non-polar molecules, then we have to realize that there is some kind of an electrical attraction between them. Okay? There's got to be a positive and a negative that are attracting each other, but they're non-polar, so how in the heck can that happen? All right, what I'm going to do now is explain to you why that can happen. And it's going to have to do with the number of electrons that are in neon and the number of electrons that are in argon. Okay? You can look this up on the periodic table. That is the number of electrons that are in each atom of these substances. Okay? All right. Now, just listen carefully to what I'm going to say now. Okay? The modern model of atoms is that electrons kind of exist as a cloud around the nuclei of atoms. So I'm drawing my laser pointer, or making my laser pointer go round and around and around each of these atoms, okay? And we've got the same thing going on around these argon atoms, okay? Now, there's nothing keeping these electrons from maybe being, let's say, heavier on one side than on the other side. They might cloud up more. If they're existing as clouds around these atoms, they might form heavier clouds in one instant than in another instant. Okay, and now remember, I want you to get that these are instantaneous moments. Boom. It's here and it's gone. It's here and it's gone. It's here and it's gone. Okay, I'm gonna highlight here, maybe in yellow, the movement of electrons around this neon, and at one point I'm going to make the neon electron cloud heavier on one side, just instantaneously. It's here and it's gone. All right, so I I'm drawing this instantaneous happening in both atoms, okay, where a positive side is developed and a negative side is developed, and in that instant, there is an attraction, okay? It just happens, okay? And the more electrons that you have, the more this is going to happen. Now, if argon has the exact same situation, these are non-polar particles, but you can have an instantaneous polarity develop. And it can happen more on the argon because it's got more electrons. So if that happens instantaneously with argon, you're going to see this happen. You're going to form a negative side and a positive side and a negative side and a positive side. But the attraction is going to be stronger between the argon, okay? So I just wrote a summary here. To summarize, with nonpolar molecules, an instantaneous dipole can develop between molecules, and we call that intermolecular force between nonpolar molecules a London dispersion force, or LDF. Okay, it has nothing to do with London, England. It's named after a guy named Fritz London, who came up with this concept. Okay, now just to also say, and keep in mind that all molecules exhibit an LDF, but it's dominant. What dominates in polar molecules is the dipole force. All right, so in other words, if there is no dipole interaction, then there is London dispersion forces at work. Okay? All right, so let's test out our understanding on London dispersion forces. I'm showing you two molecules here. These are carbon chain molecules. This is called ethane, and this is pentane. Okay, ethane versus pentane. Anyhow, you would be asked this on a test or something. Which of these is going to have a higher melting point or a higher boiling point? Or which of these will evaporate more quickly than the other one? This is all going to have to do with intermolecular forces. And since we're dealing with nonpolar molecules, okay, it's going to be the LDF that dominates, of course. So it boils down to this. Which of these molecules has a higher LDF? In other words, a greater attraction for other molecules of its kind. Okay? All right, well, you can pause at this point and try to figure that out and then come back, or I'll just keep talking. So here we go. It really comes down to if these are two nonpolar molecules, and they are, this molecule, the ethane, has fewer electrons than this pentane. Okay, so the instantaneous dipole that's going to develop will be stronger in the pentane. Okay, so I'm just going to write this out here. The LDF is stronger for that molecule. Okay, if I was to draw like two, little pictures, this could be. Let's not do that. Let's do this. This would be ethane, and this would be pentane. Okay, ethane, pentane. Okay. I could count out the electrons. I don't feel like it right now. I'm just going to say this is going to have a lot more electrons, right? Okay. So in any given instant, you could have more negative charge on this side of the molecule than the other side. And on any given moment, you could have this many, electrons, more electrons on one side than the other. Here we would have a negative side and a positive side. And here we would have a negative side. And here we would have a positive side. But this, instantaneous dipole is going to be a stronger instantaneous dipole because it's got more electrons. So the LDF is going to be stronger with the pentane. All right? The last kind of an intermolecular force that we need to talk about is hydrogen bonding. Okay? Hydrogen bonding is extremely important in biology. Okay? When it comes to biology, hydrogen bonding plays into how DNA works, how proteins are built, and how they act, how enzymes work and how they act. I mean, hydrogen bonding is just very important. In biology, you're going to hear it a lot when you take biology, okay? So what is hydrogen bonding? And I wrote it here. It's an especially strong dipole interaction or attraction that exists between molecules that contain these bonds. These bonds, a bond between nitrogen and hydrogen, a bond between oxygen and hydrogen, a bond between fluorine and hydrogen. Here are some examples of where you will see hydrogen bonding. Okay, here's ammonia, and there's the Lewis dot structure for ammonia. You can see that there are nitrogen-hydrogen bonds. Here's water. Okay, there is your hydrogen-oxygen bond. Here is hydrogen fluoride. Here is the fluorine-hydrogen bond. Okay. So when these molecules come into close proximity with other molecules of their kind, they're going to attract each other extremely strongly. Let's use water as our example. Here, let's take a look at water. Water. Okay. So, water. Okay. Let's fix that. Sorry, I made a little mistake. All right. There are two water molecules. These water molecules are going to experience a very strong attraction between each other. Okay, intermolecular force, a force between the molecules. This is what is known as a hydrogen bond. And remember, when we saw this in the simulation, it was very, very hard to separate water molecules from each other. So water has a very high melting point compared to other molecules of its size. Water has a very high boiling point compared to other molecules of its size. Okay? So hydrogen bonding, it's an extremely strong dipole interaction. Okay? I think that should do it. And I hope that was helpful. See you later.